Hello and welcome to this new video series on numerical methods for solving initial value problems for ordinary differential equations. Here we will look at some of the Tailor series and Runge-Kutta methods. In Tailor series methods, the solution of ODEs are based on the truncated Tailor series for y about x. The last term kept in the series determines the order of integration. In this case, the method that will result from this truncated series is called Tailor series method of order m. The first method that we will review is known as Euler's method. It can be viewed as a first-order Tailor series method. This means that Euler's method uses only the first two terms of the Tailor series to approximate the solution from x is equal to a to x is equal to b in n steps of size h. In this method, the approximate local truncation error is proportional to the square of the step size, whereas the global truncation error is proportional to the step size. Let's now use Euler's method to solve a first-order initial value problem on the interval from x is equal to 0 to x is equal to 4. We first define the step size h, or the number of steps n, that the algorithm will take from the starting x to final x. We saw in the previous slide that they are related such that h is equal to b minus a divided by n, where a and b are the start and end of the interval. In this case, a is equal to 0 and b is equal to 4. And after some manipulation, we can write the formula to approximate solution at each step using the value from the previous step. To implement this, we write an Euler function that takes the input function, an initial value of y at a point, the interval over which we want to approximate the solution, and the number of steps as input. On line 14, we calculate the step size. On lines 18 and 19, we set the initial x and y values, and then we start the loop, where on line 22, we use the Euler formula to approximate the solution at the next point. Then we update the x value and move to approximate the solution at next point, and we repeat these steps for all remaining points. In the main code, we import Euler function, define the function, and set the initial condition and interval over which we want to approximate the solution. And then we solve the ODE using 4 different values for the number of steps. The higher the number of steps, the smaller the step size. A smaller step size requires more computational steps, but it typically leads to more accurate result, as we can see in this figure. The solution gets closer to the true solution as n increases, which means h gets smaller. In the next video, we will review Tailor series method of higher order. Don't forget to subscribe to my channel. Thanks for watching and see you in the next video.